Good morning, everyone. Thank you for joining us. And sorry about that, we had some technical difficulties. But my name is Dr. Trena Ferrell, and I'm with the Earth Science Division at NASA Goddard Space Flight Center. And I just want to thank you all so much for all of your support during this month. We have had an amazing month of speakers, and we've got another one today. But first, I want to say thanks to our senior leaders for supporting this. I also want to give thanks to Dr. Mark Clampin, and a special thanks to Dr. Jim Irons, the Director of Earth Science. And I want to thank you all once again for supporting all of these amazing events this month. And please do not forget, we still have one more event on the 29th at 12 noon. So please join us for our final Earth Month event. So without further, I'm about to talk with you right now about our amazing speaker today. It's Dr. John Moisan, who's an oceanographer working at the Wallops Island Flight Facility, the coastal research facility of the Earth Science Division at NASA's Goddard Space Flight Center, which is located on the eastern shore of Virginia. While at NASA, he has been involved in a wide range of ocean science projects, including analysis and modeling of physical and biological interactions in marine ecosystems. Also, coupled physical biological models, just to name a few things. So without further ado, I'm going to turn it over to our amazing speaker, Dr. Moisan. And Dr. Moisan, I want to thank you very much for joining us today.
You're welcome. And thank you, Trena, for inviting me to give this talk. Today, I would just like to talk a little bit about some of the earth science activities that have been going on at Wallops for a number of years now and how they relate to climate change that we have been seeing at Wallops Island. In my outline, I'm going to go through 4 different topics, talk about some atmospheric ozone measurements, ocean surface topography, some of the sea level rise issues and inundation that Wallops Island is actually experiencing and is at risk of. And then I'm going to talk about some coastal ocean phytoplankton and how they're being impacted by climate. In terms of atmospheric monitoring, there are 4 different things that have been going on at Wallops over the years. We've had a long-term ozone time series, the AeroNet. There's an AeroNet instrument located on N159 building that has been making measurements since the mid-1990s. We've recently added a Pandora instrument. It's been added to the global network, the PGN network, and I'll talk a little bit about why that we put one in that area. And then there is, of course, the GPM, the precipitation ground CalVal instrumentation. I'm only going to talk today about some of the ozone time series and a little bit about the Pandora Global Network instrument. So let's go back to June 23rd, 1967. This is a copy of the Time magazine cover. The Israel-Arab Six-Day War had just ended, and in the cover inside you can look at the topics of Time magazine. Thurgood Marshall had just been put on the Supreme Court. Negro justice was the topic of the day. It was a long, hot summer of 1967. There were 159 race riots across the United States, but it was the summer of love. Jefferson Airplane played at the Fantasy Fair, and the opposition to the Vietnam War was in its heyday. Also that summer, Manabe and Weatherall put out a paper, Thermal Equilibrium of Atmosphere with a Given Distribution of Relative Humidity. And this was the paper that climatologists cite as being the final paper that put us on track to understand that, in fact, climate change was coming because of how much CO2 and other trace gases we were putting in the atmosphere. A doubling of the CO2 content in the atmosphere has the effect of raising the temperature of the atmosphere. Also noted the influence of changes in atmospheric ozone. On that week, ozone at Wallops was 307 Dobson units. And in fact, Wallops has been making measurements since 1967 of ozone using a Dobson instrumentation. And what you see in this figure is these measurements since that first measurement in 1967. So time is on the x-axis and total ozone in terms of Dobson units is on the y. In the late 1980s, politicians internationally got together and they put out the Montreal Protocol, which banned all of these CFC compounds that were destroying the ozone layer. If you break this time series up into the before and after Montreal Protocol, and you do a simple least squares fit that you've learned to do in high school and college, you see that we were losing ozone prior to the Montreal Protocol, and we began to gain it afterwards. To the right is actually a cumulative plot of total ozone over North America, and it demonstrates the same changes over since 1960s. We were losing ozone over North America up until a couple years after the Montreal Protocol kicked in, and then we started to gain it. We were actually healing the atmosphere. This is probably one of the only instances that I am aware of to date where policies put in internationally have made a difference in how our climate is changed. This next photo is a picture of a building, X75. It's 110 meters from the ocean at Wallops Island. The top of that building, we've just put in a Pandora instrument, and it's going to start making measurements of aerosols in the atmosphere. And I'm hoping that someday somebody gives the same talk about 4 or 5 decades worth of measurements for this instrument or instruments that follow on in that location. And the reason that we put a Pandora instrument out there is I'm intrigued by something called iodate and ozone and the interplay of them in the coastal areas. It turns out that phytoplankton live in the ocean, which, by the way, give you oxygen for your every other breath, can take up iodate in the seawater just like they take up nitrates, and they cycle it in the upper ocean. This stuff is released into the atmosphere, and we're hoping that Pandora can actually start making measurements of it. It's been seen in Skiamaki that iodate is actually released in the Southern Ocean in areas where we have large phytoplankton blooms. And so we're trying to see if we can detect this in the coastal area. And the nice thing about where we put this instrument is it's right near the Wallops Island meteorological towers. There are 3 of them. There's a 160-foot tower that measures wind increments at 50, 100, 150, a 300-foot one, and now a 730-foot tower that's going to be it's making measurements of a whole host of atmospheric constituents that we can then use to find out where the air is coming from. And if we're smart enough, we can start looking at atmospheric turbulence to maybe do some flux measurements. And I'm hoping that that's going to help with our Pandora measurements. So that's just begun. And this is a picture of these towers taken from the rooftop of where we've got the Pandora instrument. So let me talk a little bit now about some ocean surface topography measurements. Wallops' role in global sea surface topography and wave height. And this is a little bit of a history lesson. David Hancock once noted to us that Wallops Satellite Altimetry Group enabled science for many fields: oceanography, land ice, sea ice, and more. In the 1970s, Skylab S-193, a microwave altimeter, was put into space, and Joe McGugan, who worked at Wallops, worked on the design and the mission of it. It was the first ever altimeter in space. And what it observed was some of the major ocean trenches, which show up as valleys in the ocean. It had only a 15-meter resolution. The follow-on was a GO-C radar altimeter. Worked with Ray Stanley and Bill Townsend and Craig Purdy with the engineers, and the data were processed at Wallops. Interestingly enough, George Haney came into the group and started working on waveform analysis, which had a very big impact on sea surface topography measurements. Follow on to that, there was an aircraft altimeter, and then CSAT came in, which was built at Johns Hopkins, and Wallops developed the instrument. And then it went on to GeoSat. The Navy came in and started to support things, and then GeoSat follow-on. That was up until the mid-1990s. Then after that, we finally had Wallops working with CNES, the French space, and JPL, and they put together the Topex Poseidon mission. Wallops gave the main radar altimeter. It was flown by CNES, launched by the French, and JPL helped out with mission operations and data production. This was a 3-year mission with a 5-year store mission, and the mission went on for 13 years and 5 months. It had less than a half a meter accuracy. After this mission, which worked so well and gave us so much amazing observations, the Topex went on to become more of an operational satellite, and Jason 1 and 2 and 3 followed on, and today we still have operationally these topographic instruments flying in space. They've gone on to measure sea surface levels with an accuracy unprecedented. They've continuously observed the global ocean topography, the shape of the ocean, and monitored currents at a global change. They provided our first global view of seasonal changes of currents and a host of other things. When you look at, my picture here is turned 90 degrees. I don't know why. I'm hoping it's, so if you could tilt your heads, I don't know why it's turned. This is an image of the global mean sea level change that came out of all of these topographic missions. So what should have been on the X, which is now the vertical, is time in years. And now on the horizontal, which that's the mean sea level change for just that satellite. So these are satellite observed sea level changes. I'm going to go to the next one. Again, we're tilted. Why? Okay, great. So you can then take that satellite derived estimate, which is in the red here. Again, the time is on the x-axis from 1900, and the sea level rise or change in sea levels is in the y. So since the 1900s, they've gone back and done historical calculations using tide gauge data and stuff. We've seen the sea level rise in terms of rate go from 0.6 millimeters a year to actually beyond 3.5 millimeters a year. And what the satellites allowed us to do is observe the modern climate change measurements that we've got today. Let's hope that the next one is not on its side. So let me talk to you now. Now that we've got this satellite data that says, yeah, the sea level is changing, we know that Wallops Island, which is NASA's only owned and operating launch range, is at risk. I got this figure from Cynthia Rosenzweig. She was part of the Climate Adaptation Science Initiative Working Group. And this is a really good image that gives you a synopsis of the IPCC estimates that have been coming in for some time since the 1990s, looking at the climate assessment. And what you see here is the increase in resolution of these IPCC simulations. We went from the first to the fourth. And as we go to higher and higher resolutions, the hope is that we are getting better models and better data. These predictions, now the plot that I'm showing you here is time since 1990 to 2100. It's from the AR5 predictions from the IPCC. This is the predicted sea level rise in meters that we are expecting to get. They do a host of models, and we end up seeing all of the estimates from these different models that come out. So the green is the various models that they ran, the mean for global change, sea level. The blue is for standard deviation below that, 95% confidence, and the red is the 95% confidence limit above it, okay? In the blue square, I've got a note in here, a paper by Salinger in 2012. He argued that there was a hot spot that existed along the eastern shore of the United States that's 3 to 4 times higher than the observed global average, which is concerning to Wallops. And in fact, if you go back now to the time series of sea level that we got from Topex and Jason 1, 2, and 3, and you look at the trends of those sea level rises, you can create a map. And that's what you see here is a map of sea level rise detected between January 93 and January 2016. Red being a very high rate of change and a blue being a very low. So the sea level is going down. Our oceans have these things, these large-scale circulation features called gyres. And if you look at the North Atlantic, okay, you typically have what they call a cyclonic, a clockwise circulation. It's actually anticyclonic clockwise circulation, where waters move up along the east coast in something called the Gulf Stream. The sea level domes up in the center to support that circulation. A geostrophic flow, it's called. It is driven by winds. What's happened over the last 2 decades is this doming of the North Atlantic is being reduced. So the middle of the North Atlantic, where you see that blue region, is actually going down. And to compensate for that going down, the coastal areas where you see the red is coming up. That's on top of sea level rise that's due to meltwaters. This is a dynamic change. And that's what we're observing on the East Coast. And that's where we're seeing higher rates of change of sea level. You can go and get sea level rise or sea level estimates from NOAA. Here's a time series of the observed sea level at Kiptopeke, Virginia, so right near the Chesapeake Bay mouth, for 1996. There's actually 3 curves here. There's a black curve that is underlying everything. That's the actual observation. There's a blue curve, which is actually the tidal variability. And then the difference between that is the red. So think of the red as the sea level rise that you would get if there wasn't any tides. And so the big changes here are due to storm events. Okay, so you can go out and you can get this data set. And if you take that time series and you run it through a long pass filter, so only let the stuff that comes in greater than 18 months, you get this time series, and you can lay that time series out on top of the IPCC estimates. And unfortunately, what it looks like it's tracking are the red curves, or the higher estimates from the IPCC. So the East Coast is sinking, or is getting inundated faster than the global averages from the IPCC. And that's what was being mentioned earlier in that paper that I talked about. In fact, on top of that, there's a global change website that maps out in the coastal regions of the United States, all along the United States, the probability of shoreline erosion. And our eastern shore area has the highest concentration of virtually certain coastal erosion, shoreline erosion. We are at high risk of this. And unfortunately, that's where our launch range is. Wallops Island sits on a barrier island. And some of the predictions that we've obtained when you start looking at 1 foot or 2 foot sea level rise are that the island will be inundated at some level. And so there's a high risk for a very, very expensive NASA asset, its only launch range. So some time ago, I did some work for this climate adaptation science initiative, and I went and got DEM data, which is essentially it's the height of land at a 10 foot by 10 foot square for the eastern shore. And I zoomed in on Wallops Island, where I actually was able to get 1 meter by 1 meter DEM data. And using that data, so now I know the elevation of Wallops Island, I was able to actually zoom in and locate on top of Wallops Island. So that white box is zooming in the panel on the right. You can actually see the causeway, the road coming over the bridge area to Wallops Island. And all those little red numbers that you see are assets. These are buildings. And I was able to get the value of those buildings. I know how much it will cost and how much material or equipment is in each of those buildings in a spreadsheet. And I knew its elevation. What I wanted to know was, what risk were they at of getting inundated? The interesting thing is, if you start looking at sea level rise or sea level variability, here I plot now the monthly mean of the sea level rise that's been observed at that tidal gauge with the IPCC estimates. Again, you see it's tracking that the extremes of the IPCC estimate. But what's really interesting is if you go and look at the actual hourly mean sea level, you see that when you put the tides in there, you actually get a wide range of sea level variability. So what I wanted to know was, if I took that variability and I moved it on top of the IPCC estimates, what was the risk of inundation and actually how much money was at risk? I wanted to create a cost-based risk estimate up until 2100. And to do this, I went back to the IPCC estimates, and so here's a picture of what happens by 2030, how much of the island will be inundated using the worst case scenario. I said, let me create a typical building, a profile for a building. I know what the total height of a building is. And I know, for example, X505, that building has a value of 2.5 million. And I've got this digital elevation model, so I know how high it is off its base is off the ground. How can I define a building or asset cost risk? How can I create a risk? You know, how much money is on the line if we don't do anything? And the way to do that is on the right, you see this profile. The profile says, if I get sea level rise up to a certain elevation, what percentage of this building is lost? Can we just say, okay, it's gone, we've lost everything? And I can use that. I can put that then to all of the buildings and calculate what I'm going to call an elevation above 1900. What is my integrated base value in millions of dollars? Okay. I used that then with this predicted sea level variability from Kiptopeke. Okay. And I put that, so you can take that sea level and create a histogram of the sea level. It breaks apart into two pieces. The first one is this tide that you see. So you've got elevation on the x-axis and then the probability on the y for each of these. So sea level rise is all about storms and tides. Northeasters are our biggest enemy. And from this, I can take and integrate it, and you create something called a cumulative distribution function. And what that is, it allows me to do something called Monte Carlo analysis. I go back into my sea level rise, and I look at the IPCC estimates as a mean, and I put that cumulative distribution function on top of that, and I ask the question, what's the probability of an inundation event of so many feet above the 1960? And when you do that, okay, my first analysis that I did is I said, okay, look, I'm going to assume that if the building gets 2 feet of seawater in it, it's a total loss, so wall plug damage. I wasn't sure what, sea level rise was necessary to ruin a building completely, but this was our first cut. We didn't really have the profiles built for the buildings. And what you see on the right is what you call a cost-based risk analysis. Okay, now how you look at this is on the x-axis is time from 1990 to 2100. On the y-axis is millions of dollars of risk. So if I want to know in 2080, what's the risk of losing $10 million? I can just follow the $10 million line out to that 2080. It looks to be about orange, so maybe it's about 70%. 70% in 2080, I'm going to lose $10 million worth of assets on that island. Well, then you can use this type of stuff to say, well, what if I move a building up? And that's what I did. It's like, if we just took and popped all the buildings up to 10, so that they were not going to be lost 10 feet above, it drops that risk down. The risk still goes up because sea level is rising, but it doesn't go up as fast. And so I've been trying to talk to facilities folks about using this type of science-based cost risk estimator to go and when you're making decisions, do I pick up this building? Do I move this building? How much is this building worth? You can use this type of science-enabled risk analysis to manage these islands, and not just these islands, but a whole host of facilities that are at risk of inundation in the future. So, next topic. So chlorophyll A, phytoplankton diversity, climate, and coastal fisheries. This is work that I've actually been doing with some folks, Kevin Freeland at NOAA and a bunch of other colleagues, and we've just put out 2 papers on this. you can take the chlorophyll observations from satellites, and these are the papers from this are listed below. You can take chlorophyll estimates, and we're able to get from those hyperspectral absorption measurements, and we developed a technique where we can invert those to get out pigments, the different phytoplankton pigments that are out there. Once we had the pigments, there are several algorithms that have already been published in the literature that can be used to estimate different types of phytoplankton, like diatoms or dinoflagellates or cyanobacteria. And when you do that for a number of phytoplankton types, you can then look at things like diversity of the algae in the ocean. So the first paper we worked on was looking at the Northeast, and that's what those two figures are in the upper left. We're actually seeing a trend or a decrease in the amount of chlorophyll in the Northeast, and that leads to a decrease in the amount of diatoms, and decrease in the amount of dinoflagellates, and an increase in some of the cyanobacteria in those areas, but also a decrease, that second panel that you see, a decrease in the diversity of different algae types. So that was our first paper. That we went on then to say, what would happen if we did this globally, and we started to look at the large marine ecosystems that exist all around the world that are bringing fish to people's dinner plates. How are things changing when we start to look at those in a global sense? We found that if you go and look at these large marine ecosystems they've already been described in previous publications, and you do the same analysis that we did in the Northeast, we found that over 80% of these large marine ecosystems are losing chlorophyll, which means they're losing diatoms, their diversity is changing, they're getting a whole different pattern of phytoplankton. But on top of that, what we found, because we started looking at the fisheries in those areas, the same trends are being observed in catch per unit efforts. The catch per unit efforts are going up, but the yields of fisheries are not. And on top of just the chlorophyll decrease, there's been an observed pattern of increase in cloudiness. So both the temperature rise and the cloudiness seems to be impacting the level of chlorophyll in coastal systems. Okay, so now let me talk a little bit about the future and satellite algorithms using things such as artificial intelligence and machine learning. Right now, I've been funded on a project called NASA Evolutionary Programming Analytics Center, NEPAC, to try to develop these climate data records or science products and models. And this is a quad shot from that project. If you look to the upper right where the color panel is, you see something that looks like a tree diagram. This project that I've been working on actually is a machine learning, it's an artificial intelligence project that allows the computer to create equations. And then based on how good the equation is, using data to fit, to see how well, the trees are selected and then crossed, much in the way that you might do animal husbandry by picking the best plants or best animals and breeding them into the next generation. We now do that with algorithms. Initially, I developed this thing, I call it GP code, for genetic programming of ordinary differential equations. And my focus was on actually evolving coupled systems of equations for ecosystem models. And so this is just a simple set of equations for a very simple ecosystem model that models nutrients and phytoplankton and zooplankton. And in the yellow boxes, what you see is one equation that would be used in these coupled systems. And we developed a method to do this. And it was difficult because now you've got systems of equations that are coupled to each other, but we found a way to do it. And I want to show you what happens when, I'm hoping we can get this to work. When you first do this genetic programming, you end up creating a population of 10,000 or 1,000 different models. They all have a different capability, and the capability is based on some metric. That's what you see on the x-axis here, is the normalized sum of square error. So how good does each of the individuals work So this is a histogram of how good they work for generation 1. So randomly created equations, they show a histogram of capabilities just from randomly creating equations. And now, I'm hoping this works, when you move this forward and you're breeding these equations forward in time or a new generation, watch how this population of models starts to move to lower and lower sum of square errors. Now, I have to tell you that this is a twin experiment, so I already know the answer that I'm looking for in terms of the equation, and I'm tracking this. When I get to a generation that I start to see equations that are the same equations that I use to create the training data, a green line is going to pop up at the 0 sum of square errors. Is it going to work? Travis, do you think you can make that work? Oh, so great. So everyone then has seen that this histogram just basically migrated to better and better models over time. And that's the strength of this, and it happens very, very quickly. It's actually amazing how quickly it works. Can I go to the next one? Okay, so this is, hopefully it's not running, right? I want to explain this first. Okay, so if you take that picture that you just saw a movie of, those histograms, and if you could just stick them all together and then colorize the peaks, and you would create this histogram, or you would create this bitmap. And what you see from this bitmap on the x-axis are the generations, and now the histogram is colorized, so red is high values, and the sum of square errors is the histograms you're seeing on the y-axis. And what you saw earlier, that migration occurs, that's that drop into the lower left of values to the very low sum of square errors. The solid red line that is in this image is the generation number that I get when I finally have the model that I used to generate the data. So it tells me when I found the correct model. And this is great to do when you've got a twin experiment, when you know the equations, what the equations are that you use to generate the data. But in reality, we don't have that. When we go out in the field and we make measurements, either using a satellite or a ship, we don't know what the equations are. Okay, so I wanted to know what happens if I keep rerunning this. Go ahead, run that now. Okay, so what you see here is the variability in the number of generations that it takes to get a twin experiment to conclude I've got the model that I used to create the data. When you're doing this with real data, you don't know when you've got the right model. So you don't know how many generations that you need to go and evolve through until you finally get the model that you like. And the point for all of this is that you never will. Keep in mind, these are models. There's no real true solution when you have real data. Okay, let's see, one more. So presently, we are focusing on taking the ocean color measurements for remote sensing reflectance. And we're working on creating an algorithm for chlorophyll, just chlorophyll. And we've run a number of cases, and the outputs that we get look like this. This is the outputs from just one simulation. And we're trying to do this. The whole point of the AIST project is to containerize everything so that a researcher can pick this up and put it on their computer systems and go and get their own chlorophyll observations, retrieve the satellite observations, and create their own algorithm. Maybe they're working in a bay. You know, it's unlike the Chesapeake, some bay, who knows where, Bay of Bengal or whatever. So if you look at the lower left panel, I'm comparing two different algorithms. On the bottom, the green dots, I'm comparing the OC4 algorithm, and this is linear scale. So using this thing called the IOCCG chlorophyll data. And you see that the actual chlorophyll values are very widely ranging when you look at the linear scale. If you go to log scale, things look better, which is just above it in the blue. To the right is a comparison, again, comparing a run of this GP code that gave us a much more improved model than we got, or an algorithm, than we had for the OC4. And in fact, the set of panels to the right are actually images of this code that we're running. So the two left panels that you see, the bitmaps, look at generation numbers, and I'm plotting the value for the mean average percent error on the top and the sum of square errors on the bottom. And when I do a histogram of those, that's what you see on the right. And the thing I want you to note on these histograms, again, they drop with time. The values drop to these low values. I plotted the OC4 algorithm, mean average percent errors and sum of square errors, with a horizontal red line. And the reason I did that, I wanted to demonstrate that we're actually able to get almost an order of magnitude improvement using a computer for algorithms for chlorophyll right now. And so I'm going to show you what that looks like in terms of comparing a bunch of different runs. This is a Taylor plot that compares normalized standard deviation. So this black dot is on the bottom axis at the value 1, is actually the observations. And I actually zoom in on that little spot to the right. So you see a zoomed in spot to the right. The blue line that you see, the curve, is what happens when you take and you fit an OC4-like equation. So what that is basically band ratios that are put into a second, third, fourth, and fifth order polynomial. And I just wanted to show what the spread of increases in capability were if you went to higher order polynomials. Okay, so that's the range if you put in a fourth, fifth order polynomial. So that's kind of like the OC4 family of algorithms. The numbers that you see in magenta and green, these are just different GP code runs. And the little black numbers that are next to them are the number of coefficients in those algorithms. One of the complaints that has been thrown at AI is that AI is just an overfitting tool and you really don't know what's going on when you start using them. We're really trying our best to remove the problem of overfitting. But interestingly enough, if you look at that blue line, there's a case 16. That case is the only one that I've come across so far. It has 0 parameters in it. It's only using satellite observations. Only using satellite observations. Is that an overfit? I don't know what that means at that point when you have 0 parameters. Some of the others have 2 or 6, and some of them are 18 parameters. And the idea being is that the more parameters, the more degrees of freedom you have, the more likely you're going to have an overfit of the data. But that's where we are at in terms of trying to develop a better chlorophyll product that we can then use to maybe approach the agency to come up with a better climate data record using artificial intelligence. And that's the end of my talk, and thank you for your time.
Wow, what an interesting talk. Thank you so much. A virtual round of applause. Very interesting. Thank you so much. Great talk. So if you have any questions, anyone, please type them into the chat box. Okay, great. So thank you very much. And Travis, can you read the question since I'm not seeing it in the chat box?
Yeah, no problem. So, John, how does loss of beach to increased erosion as the ocean moves west affect resulting damage analysis?
As the beach moves, well, they keep putting in a beach, so it hasn't moved west yet. So I'm just looking at DEMs here and inundation. We haven't looked at any change in topography. We haven't tried to look at a loss of land due to beach erosion. The truth is, in terms of risk, it's the northeasters and the hurricanes that do the damage on the island. And the risk of that damage increases with sea level rise. The one that everyone's really concerned about, or should be if they're not, is behind the beach, the marshes. We know that marshes can grow. If you slowly increase the sea level, they'll actually grow. and maintain themselves. But what we don't know is how fast the sea level rise they're able to, tolerate before they actually give it up. And if the marshes go, that's mud, and that's pretty unstable if it's not growing.
Thank you so much again for this excellent talk. We really, really appreciate it. A virtual round of applause. Thank you everyone for joining us today, and please join us again for our last and final talk this week. Thank you very much, everyone. Stay safe.
Thank you all.